In the previous two episodes, we have discussed Juergens Electric Sun Model, describing in detail how the granules on the Sun can be linked to anode tufting, and explaining in detail the mechanism that sits behind this. In part 2, we looked at how this electric sun will be connected to the larger galactic framework. We noted that Juergens had made several assumptions which we now know are not correct, but the model has since been modified by the EU community to overcome these problems. In the next few episodes, I want to explore how the EU have taken this idea and gone beyond Juergens' electric sun model. In the first part, we will be talking to Wal Thornhill and discussing how he became involved with the concept and how he identified some specific areas that needed refinement, including the concept of transmutation as a source of some of the radiant energy of the Sun. In the fourth part of the series, we will continue to talk to Wal Thornhill and discuss the differences between the solar environment in the two models, and look at how the Birkeland currents play a crucial role in enhancing this model. So, Wal, how did you come across the Juergens model way back when?
Well, it was back in 1972 in an issue of the Ponce journal, where he just wrote, I think he said, I don't know of any other way to put this other than bluntly, and that is that almost every aspect that we see of the Sun defies the thermonuclear model. And when I thought about that, I thought, he's right. You know, if it's just generating heat in the center of the star, that heat should be trying to escape, and all of these things like the corona and the chromosphere and spicules and jets and granulations shouldn't be there. And it wasn't until a little while later that he actually put forward his full model. But his arguments in that very first article were pretty persuasive. I'll send you actually the material that you can use in the for your screen, quotes from him and so on. Yeah, but in 1972, having read Juergens' first attack on the thermonuclear model of the Sun, and done in quite a convincing manner, I was on the lookout for anything and everything that I could get my hands on to try and take that further, see what could be done with it. When he came out with his detailed model, I realized that he'd done an amazing job of looking at what's known as a low-pressure gas discharge. And that's a very specific phenomenon observed in the laboratory and studied quite carefully, both in the late 1800s and early 1900s. And it's quite complex. And that was the fascinating part, because Juergens was able to, I think the genius that he brought to this was that he was able to identify all of the features on the Sun, all the main features, forget about sunspots and that for the moment, the blemishes, but the granulations, the spicules, the chromosphere, the corona, everything in terms of his electrical model, electric discharge model. And that raised the interesting question, well, if it's not a thermonuclear sun, is the electricity enough to light it? And so he calculated what would be required, and the figures came out quite high, but they weren't beyond the realm of possibility. You have to remember, back in 1972, we had no idea where the boundary of the Sun's electrical influence would be. He suggested it might be out, maybe past Jupiter or something. But we now know that it's at 100 astronomical units away, which is well beyond Pluto. And the two Voyager spacecraft are the only spacecraft that have managed to get to that boundary. One of the interesting aspects of that particular, or those Voyager spacecraft reaching that boundary, was that I was looking for something that others weren't looking for, and that was a slowdown in the solar wind, because according to the gas discharge model, the field reverses just before you get to the cathode drop, which meant that the solar wind, the protons, would be slowed down, and that was discovered. So that was a very good sign that Juergens' model was correct. The big difference being the huge diameter of this heliosphere. That was my first introduction to it. In that article in 1972, Juergens referenced an Englishman, Dr. Charles Bruce, who was both a Fellow of the Royal Astronomical Society as well as being a Doctor of Electrical Engineering, and in particular, lightning, the phenomena of lightning. So here we had a fellow who was well versed in electrical discharges, and was also very active in astronomy at the same time. And he published a number of articles extending back to, I think it was about 1945, where he looked at the sun, the appearance of the sun, as being an electrical discharge phenomenon. And in fact, I've got a document of his right here in 1957 called Cosmic Thunderstorms, where he goes into some detail about how he thinks stars are lit and why their spectra appear the way they do. And of course, it is a very simplifying model, because when you look at stars, it's not the case of evolution, slow evolution over time, where certain elements are produced in the thermonuclear engine, and they increasingly appear in the photosphere. But if you look at that carefully, it's very hard to explain a lot of the spectra that we do see. And also, there are a lot of stars that seem to change almost overnight from one part of the Hertzsprung-Russell diagram to another, which defies the slow evolution model. So that was it. I saw Ralph Juergens. I didn't actually get to speak to him at the 1974 conference in at McMaster University in Hamilton, Ontario. It was a big deal for me because I'd cashed in insurance policies and everything and took my wife with me, and I'd made myself known, though, to Stephen Talbot, David Talbot's brother, who was one of the chief organisers of that conference, and he invited me to come based on the work that I'd been doing, and I actually got to meet Velikovsky, which was great. I think he referred to me in the final evening, the banquet speech where he said, people have come from the ends of the world. I thought, oh, that's me. Yeah, I was very impressed at that meeting, by the way, because Ralph Juergens had published more material on the scarring of Mars and the Moon, and he was presenting that material. And once again, his research is very detailed and very thorough. And it was a real scientist's approach to the problems. And so I've got to at least see or meet most of the people involved in the early history of all of this.
So then you sort of took that model and I mean, obviously, as we talked about in the previous episode, there are certain assumptions that Juergens made in his model, which today we think is wrong is maybe the wrong word, but is the wrong assumption to use in that model.
Yes, he did actually suggest that the electrical energies involved in his model would be sufficient to cause fusion in the photosphere. But he had nothing really to work on at that stage to make any suggestions about details in that area. It was merely a suggestion. In the late 70s, at my work, people knew the sort of interests I had, and one of the fellows came up to me and he said, have you read any of Professor Louis Kervran's work on biological transmutations? And I said, no, I've never heard of him. So he lent me some books. And the appeal of those books was instantaneous because Louis Kervran, it turns out, was quite a famous French scientist and a very good experimental scientist as well. And he had done experiments, simple experiments that you could even perform in a high school lab, and I hope they do in future, where you use a thiobacillus, for instance, which is associated with sulfur. That's where the thio comes from. And you put it in a test tube with a tiny microscopic amount of sulfur, and you can measure the amount of sulfur you put in, and then put it in the incubator with some water, and you come back later and the entire inner surface of the tube is covered with sulfur. What it is doing is transmuting the oxygen in the water to sulfur, because that transition is a fairly low energy nuclear one, but it seems that biological systems are capable of performing these minor miracles. Well, I then bought his books, and I've read quite a bit of them, not recently, but I realised that I could go about looking at the Dave Talbot's history of the Earth and Saturn and Mercury, Mars, and so on, and Venus, and consider their atmospheres and have a look to see whether I could explain, in Louis Kerr-Rand's term, the atmosphere of Venus. Now, that was a challenge. I mean, it's the most unearthly atmosphere, and yet it's supposed to be a twin planet. Velikovsky had successfully made the outrageous prediction that Venus would be found to be almost incandescently hot, which was not on anyone's radar at the time, and yet he was proven true. So when they sent the spacecraft, the Russian landers and the US spacecraft into the Venusian atmosphere, I found that you had a very heavy carbon dioxide atmosphere, very little water, and what water there was disappeared as you got closer to the surface, and there was about 4% nitrogen. Even that amount of nitrogen, that was 4 times more than the Earth has got in its atmosphere. So there's a lot of nitrogen as well. So one of the introductory bits of research that Louis Kerr-Rand did was to look at carbon monoxide poisoning in welders. People who were welding and they didn't have exhaust fans and so on were suffering carbon monoxide poisoning. And he was asked, I think, by the French government to look into it. And he finally recognized that you could not detect any carbon monoxide in the atmosphere, but when these fellows breathed in this nitrogen, it was being converted into carbon monoxide. In other words, the biological substrate was the catalyst, if you like, for a nitrogen molecule which had its energy had been boosted. It has to be above 400 degrees Celsius, I think, red heat, before this happens. And it also explained, he said, in his childhood he'd gone to school and found that they had a heater, an iron heater in the room, and with all the closed windows and the cold weather, the kids started to complain of headaches and that, and the teachers knew that they had to open the windows to relieve the effects. In other words, it's one of the symptoms of carbon monoxide poisoning. One of the first symptoms. It's very insidious, actually. A lot of people die from carbon monoxide poisoning without recognizing that it's the heater in the room that's causing the trouble. So I had this notion that we could actually have nuclear reactions at lower energies. And at that stage, it was open then to having a lower energy source for the sun, lower electrical energy, to produce these nuclear reactions. And
just to be clear, why is that important? Why is it important to have a lower energy source? So why would the fact that nuclear reactions take less energy be important to that model?
Well, one of the reasons is that we know that nuclear reactions take place on the sun simply because of the neutrinos that come from it. But for decades, they could never detect the number of the kind of neutrinos that they should have observed. They came up with a trick that the particle physicists gave them to say that they just change in flavour. I love these words, flavour. What does that mean?
Yeah.
Anyway, but it didn't prove anything. It was just a suggestion, and it still is only a suggestion because you can't tell unless you have a detector somewhere between us and the sun as well. Anyway, with these low energy nuclear transmutations, because these are, you could call them fusion, but it's low energy fusion, cold fusion almost, or warm fusion. Yeah, the importance of that for the sun was that we know that there are a lot of heavier elements in the spectrum. And the simplest answer for Juergens' model is that they're being generated in the photosphere itself. But Juergens' model, even though it invokes relativistic electrons as a possible boost to the energy, the electrical energy, it seemed to me to be a rather brute force and ignorance approach instead of something that's more subtle. Because throughout my career, I've always felt that nature knows how to do things the best way possible, and we've got to observe it and take careful notice because we're unlikely to be able to improve on it. In 1981, I became alerted to the work of Ralph Sansbury, and that was the structured electron. And I corresponded with him, and I met him in London, actually, when he was passing through, and visited him at his home in upstate New York. And his model of the electron, interestingly enough, was just to say, why don't we repeat the very successful atomic orbital model and say electrons and protons, the subatomic particles themselves, are orbital systems. Now, this to me, on looking back, is just so obvious that it's mind-boggling that the particle physicists invoked the old plum pudding model of J.J. Thomson.
Yeah.
They did it again. They didn't learn from history. Anyway, with this very simple model, you realize that the Coulomb law or the Coulomb barrier is not a fixed barrier. It's an electrodynamic thing. In fact, can be actually attractive if you just get in the rhythm. And this is it. It's all about resonances. And when you're talking about resonances in physical chemistry, it's all about having a catalyst. So what we're talking about is nuclear plasma chemistry. Forget to talk about fusion and thermonuclear and all that stuff. This is nuclear chemistry in the plasma.
So physically changing the structure of the atom at low energies. That's effectively what we're talking about here.
Yes, we're doing it in nature's way, which is very simple. Biological systems can do it at even room temperature or lower temperatures. The sun does it at a higher temperature and is possibly the most effective way of producing a vast range of elements, which we're now interested in discovering in our SAPPHIRE experiment.
Which is what we see when we look at the sun. We see that the metals and other elements in effectively the atmosphere, because we obviously cannot see below the surface. And obviously the current model assumes that comes from deep within. But what we're suggesting is that actually these are produced in that sort of discharge reaction around the, I don't want to call it atmosphere, but that sort of photosphere to the chromosphere and beyond area.
That's right.
What implication does that have? Because obviously in Juergens' model, he had to have these relativistic electrons to give enough sort of smash to generate enough energy. And he saw the cathode drop as being, I think off the top of my head, 10 to the power of 10 volts.
Yes.
If we don't require all of that energy to come from those electrons, what does that cathode drop look like in the EU model?
Well, for instance, it has been detected by spacecraft that there are a series of double layers between us and the sun, and the double layers are those regions of the plasma that contain an appreciable electric field. The positive, they call it the positive glow region of the discharge, which fills most of the solar system, if you like, right out to the heliosphere. In that region, the electrons are merely drifting, I think, as you showed in a previous episode, and they're collected at the anode. that means that this is one of the reservations I had about Juergens' model, was this positive region. When they were sending spacecraft up, they weren't detecting relativistic electrons. I mean, they're pretty easy to detect. And since they weren't, I felt, well, the positive column must extend from fairly close to the sun right out to the boundary, 100 AU or so, in which case we will not see relativistic electrons. Now, right up close to the sun, of course, they can be accelerated to higher energies. But even our SAPPHIRE experiment is tending to show that even in the double layers themselves, we have sufficient energy to perform some of these transmutations. Which was, I mean, all of this is new stuff. I was the one who advised about looking for nuclear transmutations, and that the experiment was designed specifically, and one of the major things was to check for that. And that was the reason that Monty wouldn't go public with a success story until that was proven.
Which is why it took a bit longer.
Yes, and that was a big moment for me.
Yeah, I'll bet. But what does it mean in terms of the EU model? What would you see that cathode? I mean, obviously, we don't necessarily know an exact figure, but obviously 10 to the 10 volts is an extremely large potential drop. And obviously, if transmutation is occurring at the sun, it means that not all of the energy needs to have come from that potential drop. So what, in your mind, where would we put a ballpark figure on that potential drop in the EU model?
Well, instead of 10 to the 10 volts, that figure between the Earth and the sun that was estimated from spacecraft measurements was about 600 volts. So that's 1 AU. If you go out to 100 AU, it'll be 100 times 600. That's not much.
No, but it's still significant. It's still
significant, of course, yes, and you must have it, otherwise the drift current doesn't exist.
In the next part, we will continue to talk to Wal about the solar environment and discuss how the Birkeland currents are connected to the sun and how this changes the model from the one originally proposed by Juergens. Beyond this, I would like to explore in more detail how the EU community have gone about providing more detail about the internal structure and discuss some of the features we observe on the sun and relate them to specific mechanisms. If you are interested in the full version of the discussion that I had with Wal, this will be available on my Patreon page to all my Patreon supporters. If you are interested in becoming a patron, then please see the link in the description for that. Without this support, it would not be possible to create these videos, so a massive thank you to all those who continue to support this channel through Patreon and those that make direct donations via PayPal. As always, be brave, be curious, the truth is waiting for us. Until next time.